Section 16.1 is on page 969, talks about line integrals. This is something we're going to use all throughout this chapter. This definition, we start with, let f be a defined on curve C, parametrically, by a parametric equation. F is traced by R of t, in which g of t for the I component, h of t for the j, and k of t for the h. And let t vary between a and b. Then the line integral of f over c, and that's how we write it. The line integral of f over c. This is simply x of t, y of t, and z of t, and here they are. And from section 11.1, we know what ds is. We spent a long time deriving that back in the days, right? In 1150, ds is the magnitude of v of t, which is the magnitude of r prime of t, or simply, if you recall, ds was the square root of dx dt squared plus dy dt squared plus dz dt squared, right? And there it is. This is the magnitude of r prime if this is r. Oh, you have to convert x to g, y to h, and z to k. So, from 11.1 and 11.2, we know what ds is. It's right there. Right? And we know the magnitude of r prime of t. If I take a derivative of that, that is simply the ds they're talking about. Now, something I want to add. If you want to find a piece of a line, if you want to find a piece of a line segment running from A to B, this was a formula given in the previous course. This is provided you're running from R sub 0 to R sub 1, and if this is what you use, you're going to set t to be between 0 and 1 every time. This is the equation of a line segment, a line running from R sub 0 to R sub 1. And I'll point that out as we do this in case you've forgotten how this works. And the way it works, this right here, if I take this f of t and multiply that by the magnitude, that turns out to be the area. So there is a nice figure in the book I want to point out. Where did it go? Let me find it. And this kind of shows you visually if f of xy, which is z, is bigger than or equal to 0, then the integral along c, there's c right there, the red, will end up, when you're integrating and multiplying by ds, will end up finding like the area of that fence right there, depending on how high is z in different places. Now we want to look at some problems and apply those. Here on page 974, they want us to match. They say match each vector with those 8 graphs, and the reason I have them on the right because we're not going to really use the graphs. We're going to more like look at the 3D ourselves and start practicing how to graph those, because we need to do that on the long run. If I look at this vector says 1, 1, t, and t varies between -1 and 1. That's saying x equal 1, there's x equal 1, y equal 1, there's y equal 1. So you are stuck at that point. And it says z runs between -1 and 1. Doesn't that indicate that you're talking about this? So if I glance at these graphs, kind of eyeball which ones, I notice this is E. So not only are you going to match, I want you to really graph those, because we're going there anyways. Not only are we going to graph them, we're going to do a lot more than that. Next, we're going to look at this, and this is t0, 0. There is no j, no k. Well, that means you are really not shifting left or right or up or down. You're stuck right there. But it seems the I component is running from -1 to 1. So you're really stuck in that direction. And if I glance at those, this matches A. And if I get to the next problem, I'll be looking at t and 2 minus 2t. Again, since t is linear, this is a piece of a line. At t equals 0, I would be at 0, 2. Well, 0, 2, I forgot to get the grid going. So initially, I am at 0, 2. Oh, 0, 2, 0. I'm sorry, this is 3D. I forgot about that. 0, 2, 0. So if I move to 0, oh my god, I messed up the problem. I'm sorry, let's do it again. So this is 0, t, and 2 minus 2t. Look at that. At t equals 0, r of 0 is actually 0, 0, 2. Should have erased that. Oh, come on. I really need time. So if I match this, I am looking at 0, 0, 2, 0, 0, 1, 2. This is where I start. And I terminate at t equal 1, just like we did back in the days. So that will be at 0, 1, 0, 0, 1, 0, I'm sorry, 0, 1, 0. So I'm really moving in this direction. And I'll try to match which of those, and it's right there. If this turns out to be B. 8 is something you really want to pay attention to. That's something that we need heavily. That is twice the cosine of t, twice the sine of t. And if you recall when we did this, when we played with this back in the days, we said x equal twice the cosine of t. So x squared over 4 equal cosine squared of t, and y squared over 4 equals sine squared of t. And if we added those, we got x squared over 4 plus y squared over 4 equal 1, which is a piece of a circle. Now, I noticed that I and k, I and k, so this is really z. So, I have a circle wrapped in the xz plane. So let me get this going. Something that we're going to have to play with a bit more than we like because of the applications, not because of anything else. And if you remember, I needed direction. So if I would go ahead, I know that right here, y is fixed at the origin. So you're not moving left or right, but you're moving 2 up, 2 down, 2 forward, 2 backwards. And you're looking at something like this. Kind of hard to do. I should have did the circle first to label it out. Oops, not that much. Okay, so this is 2, this is 2, this is 2, and this is 2, right? But it is fixed at the origin. But I need direction. At t equals 0, I will be at 2, 0. 2, 0, I'm right here. At t equal pi over 2, I would be at, oh man, come on. I would be at 2, 0, 0. I would be at 0, 0, 2. 0, 0, 2, I'm right here, so I trace this upper half. And at t equal pi, I would be at -2, 0, 0. negative 2, 0, 0 is right there. So I notice that I only trace the upper half of that circle. And that would match H. So here the one is the match. We want a bit more than matching. We want really graph those, because that's something we're going to have to do soon enough. So everything that you learned, you're putting together now. Now we want to apply this theorem that we talked about. If I'm talking about the integral of f of x, y, z, which is evaluating a line integral, the line integral, and here it is, over c of x minus y plus z minus 2 ds. Well, I need two components. One, that's going to be the integral, and I notice x is a t, y is 1 minus t, and z is a 1 minus 2. ds I need to figure out. Well, ds is the square root of dx dt squared plus dy dt squared plus dz dt squared. Now something I want to point out. I could do it that way, but I really recommend that you actually start writing this down, because pretty soon it's not going to be a constant. Write what RFT is. RFT is defined by t, 1 minus t, and a 1. So, oh boy, I even messed up. That's a 0 and that's a negative 1. Man, you all see the benefit of that. Right? So, when I take the magnitude of ds, that is, I take r prime of t, that would be 1, negative 1, 0, and ds is actually the magnitude of that vector, and that's what ds is. Alright? And the dt is really part of the problem, not part of this. So this is going to be f times a magnitude, the square root of, what is that? Isn't that 2 dt? And by the way, if I'm given r of t, the velocity function is r prime of t, in case you were wondering. I mentioned that back in the days, but probably you overlooked it or you didn't see it. Not a big deal. Now I have one more thing to worry about. I need to know what the limits are. Well, look at that. I need to know t varies between what and what. Keep in mind how this works. Since you could pick any of those, since x is bound by t, all what I have to do is look at the x values, and that should do it. And I could do this in any order. In this case, it seems to be running between 0 and 1. And that integral is really simple to do. That is the integral from 0 to 1. Radical 2 is a constant. This is 1 minus 1 plus t minus 1. So that is t minus 1, if I'm not mistaken. Let me check. That's a t. So that's 2t minus 2 dt. And I take it you could work it out from here on, right? Add in the hard side of that, plug the values in, and so on and so forth, and you get the answer. Alright, and the answer turns out to be negative radical 2. I'm getting that from my notes. I'm trying to do as many evens as possible. If I run into an integral that really is